November 11, 1944, Vladivostok, Soviet Far East. Captain Howard Jarrell brings his crippled B-29 Superfortress down on a Soviet airfield after a bombing raid on Japanese-occupied Manchuria, trailing smoke from battle damage and running dangerously low on fuel after the long flight from bases in China. And he expects that Soviet forces will provide assistance and allow his crew to return to American control, because the Soviet Union and the United States are allies fighting the same enemies. What Gerald doesn't know, as Soviet troops surround his aircraft and Soviet officers politely but firmly inform him and his crew that they're being interned, is that his B-29 will never leave Soviet territory, that Joseph Stalin has already issued orders that any American B-29s that land in Soviet-controlled areas are to be seized and held regardless of diplomatic protests, and that this particular aircraft is about to become the subject of the most ambitious reverse engineering project in Soviet history. Stalin understands that the B-29 represents American technological capabilities that are years ahead of Soviet aviation, and he recognizes that possessing similar strategic bombing capability would fundamentally alter the balance of power in the post-war world that's rapidly approaching, as Germany collapses and Japan weakens under relentless American air and naval assault. The Soviet Union has adequate tactical bombers for supporting ground operations, but nothing remotely comparable to the B-29's combination of range, altitude capability, payload capacity, and defensive armament. And Stalin knows that in the emerging confrontation with the Western powers that he anticipates after Germany's defeat, strategic bombing capability that can threaten enemy industrial centers and cities from bases deep inside Soviet territory will be essential for deterrence and for projecting Soviet power globally. By mid-1945, 3 B-29s have made emergency landings in Soviet territory under various circumstances, and while American diplomats protest and demand the aircraft and crews be returned, Stalin refuses and instead orders the aircraft transported to Moscow, where Soviet aviation engineers and designers can examine them in detail. The crews are eventually repatriated through complex negotiations, but the aircraft remain in Soviet hands, and in July 1945, Stalin summons Andrei Tupolev, the Soviet Union's most accomplished aircraft designer and head of a major design bureau, to the Kremlin, and gives him an assignment that seems impossible: reverse engineer the B-29 completely, create exact copies that Soviet factories can manufacture, and have the first examples ready for flight testing within 2 years. Tupolev's initial reaction, which he's careful not to voice directly to Stalin, is that the task is impossible within the time frame, because creating an exact copy of an aircraft as complex as the B-29 requires not just understanding how it works, but also replicating thousands of components, many of which use materials, manufacturing processes, and technologies that don't exist in Soviet industry. The B-29 is arguably the most technologically advanced aircraft in the world, with pressurized crew compartments that allow operations at altitudes above 30,000 feet, remote-controlled defensive gun turrets with sophisticated fire control systems, engines producing 2,200 horsepower each using technologies Soviet engine designers haven't mastered, and systems integration that represents American industrial capabilities at their peak. But Stalin makes clear that failure is not acceptable. The Tupolev has whatever resources the Soviet state can provide, and the producing Soviet copies of the B-29 is a top priority that will receive support at the highest levels, regardless of cost or difficulty. The examination of the 3 captured B-29s begins at the Central Aerohydrodynamic Institute near Moscow, where Soviet aviation experts, metallurgists, engineers, and specialists in various technical fields assemble to systematically document and analyze every aspect of the aircraft's design. And what they discover confirms Tupolev's concerns about the magnitude of the challenge. The B-29 is constructed using thousands of precisely manufactured aluminum components held together by hundreds of thousands of rivets. And the aircraft uses measurement systems, material specifications, and manufacturing tolerances that are fundamentally different from Soviet practice, creating immediate problems that must be solved before reverse engineering can even begin. The first major obstacle Soviet engineers encounter is that American aircraft are designed using imperial measurements, inches, feet, pounds, while Soviet industry uses the metric system exclusively, and every dimension, every hole spacing, every component size must be converted from imperial to metric while maintaining the precise relationships that make the aircraft function correctly. This conversion isn't simply a matter of mathematical calculation, because manufacturing tolerances and part interchangeability requirements mean that some dimensions must be rounded differently than others to ensure that Soviet-manufactured components will fit together properly. And Soviet engineers spend weeks developing conversion protocols that will allow accurate translation of American imperial specifications into Soviet metric equivalents, without introducing errors that would cause parts to not fit or systems to malfunction. The metallurgical examination reveals even more daunting challenges, because the B-29 structure uses aluminum alloys with specific strength and weight characteristics that Soviet metallurgists don't have formulas for producing, and American practice marks alloys with designation systems that don't correspond to Soviet systems, requiring chemical analysis of samples from the captured aircraft to determine exact composition. Soviet metallurgists discover that several critical aluminum alloys used in the B-29 structure have higher strength-to-weight ratios than comparable Soviet alloys, and that American manufacturers have achieved this through alloying elements and heat treatment processes that Soviet industry hasn't developed, creating an immediate crisis because simply substituting available Soviet alloys would make the aircraft heavier and potentially compromise structural integrity. The solution requires Soviet metallurgical institutes to develop new aluminum alloys that match American specifications closely enough that components made from Soviet materials will perform adequately. And this development process involves months of experimentation, testing, and production scale-up to create alloys that Soviet factories can manufacture consistently. The metallurgists eventually succeed in developing Soviet equivalents for most American alloys, though some Soviet alloys end up slightly heavier or having different working characteristics that require compensating adjustments in other areas of the design. And the entire metallurgical effort represents a crash program that advances Soviet aluminum technology by several years in just months of intense focused work. When Soviet engineers begin detailed examination of the B-29 systems, they discover level after level of sophistication that exceeds Soviet aviation practice, and each system presents unique reverse engineering challenges that require innovative solutions. The pressurization system that maintains cabin pressure equivalent to 8,000 feet altitude, while the aircraft operates at 30,000 feet or higher, uses compressors, pressure regulators, and sealed bulkheads that Soviet aircraft designers have never implemented, because Soviet bombers don't operate at altitudes where pressurization is necessary. And Soviet engineers must learn not just how the American system works, but also how to manufacture the complex curved pressure bulkheads that separate pressurized crew compartments from unpressurized sections of the aircraft. The remote-controlled gun turret system represents perhaps the most complex electromechanical system Soviet engineers encounter, and understanding how it works requires disassembling the turrets, tracing electrical circuits, analyzing the mechanical linkages that translate gunner inputs into turret movements, and comprehending the fire control computing system that automatically calculates lead angles based on target motion and ballistic characteristics. The B-29 uses a sophisticated system where gunners sit at remote sighting stations inside the pressurized fuselage and control turrets mounted externally through electrical connections, and the computing system uses analog mechanical computers that perform ballistic calculations in real time, technology that Soviet aviation has never attempted to implement and which requires developing entirely new manufacturing capabilities to replicate. Soviet engineers discover that the B-29's Wright R-3350 engines incorporate numerous advanced features, including sophisticated supercharging systems that maintain power output at high altitudes, fuel injection systems that provide precise fuel metering, and complex ignition systems with redundancy that American designers built in for reliability. Soviet engine designers examine the R-3350 in exhaustive detail and conclude that directly copying the American engine would require developing new manufacturing processes for components like cylinders, crankshafts, and supercharger impellers that Soviet factories don't currently have capabilities to produce. And instead, they decide to use the best available Soviet radial engines, the Ash-73 developed by Arkady Shvetsov, while modifying them to incorporate whatever R-3350 features can be adapted to Soviet manufacturing capabilities. As Soviet engineers work through the systematic documentation of every B-29 component, they develop detailed technical drawings that translate American imperial dimensions into Soviet metric equivalents while preserving the functional relationships between components, and this documentation effort eventually produces more than 100,000 engineering drawings covering everything from major structural assemblies to individual fasteners and electrical connectors. The drawing effort reveals another challenge. American manufacturing practice uses different standards for technical drawings than Soviet practice, with different conventions for indicating tolerances, surface finishes, and assembly relationships. And Soviet engineers must translate not just dimensions, but also manufacturing intent from American conventions into Soviet equivalents that Soviet factory workers and technicians will understand. Stalin's directive to create an exact copy rather than an improved Soviet variant creates both challenges and advantages for the reverse engineering effort, and Tupolev's team debates whether copying American features that seem suboptimal or could be improved makes sense. But ultimately, Stalin's order is clear. Copy everything exactly, including features that seem unnecessary or inefficient, because the Americans presumably had reasons for their design choices, even if Soviet engineers don't immediately understand them. This directive means that Soviet engineers must replicate even apparent manufacturing defects and anomalies found on the captured aircraft. And there are numerous cases where Soviet engineers discover what appear to be mistakes or odd features and want to correct them, but are ordered to copy exactly as found, because distinguishing between intentional design features and actual errors is difficult without understanding American design intent. The manufacturing challenge of actually producing Soviet copies of the B-29 proves as difficult as the reverse engineering, because Soviet aircraft factories are set up for producing much simpler aircraft using different construction methods and materials, and converting factories to B-29 production requires massive retooling, new equipment, worker retraining, and development of new quality control procedures to ensure that Soviet-manufactured components meet the tight tolerances that the B-29's design requires. Soviet factory managers, accustomed to relatively crude manufacturing tolerances and acceptance of significant variation between individual aircraft, struggle with American requirements for precision and interchangeability. And quality control becomes a major focus as Tupolev's organization works to ensure that Soviet factories can consistently produce components that match American specifications. The electrical and electronic systems on the B-29 present particularly difficult challenges because American practice uses components and manufacturing techniques that are more sophisticated than Soviet electronics industry standard practice. And Soviet engineers must either develop equivalent components or redesign systems to use available Soviet electronics while maintaining functional equivalence. The radio systems, radar equipment, and various electrical instruments use vacuum tubes, resistors, capacitors, and other components with specifications that Soviet electronics factories don't routinely produce. And in many cases, Soviet engineers must work with electronics manufacturers to develop new component types or modify existing designs to meet B-29 requirements, creating ripple effects throughout Soviet electronics industry as manufacturers upgrade capabilities to support the bomber program. As the reverse engineering progresses through 1946 and into 1947, Soviet engineers gradually solve the technical challenges one by one through combination of direct copying where possible, adaptation of American designs to Soviet manufacturing capabilities where necessary, and occasional innovation, where Soviet engineers develop their own solutions to problems that they can't solve through direct replication. The result is an aircraft that Tupolev designates the Tu-4, and which is externally almost identical to the B-29, but which internally contains mixture of exact copies of American components, Soviet equivalents that perform the same functions using different approaches, and occasional Soviet innovations where engineers found better solutions than direct copying would provide. The first Tu-4 prototype flies in May 1947, meeting Stalin's 2-year deadline, though just barely. And test pilots report that the aircraft performs remarkably similarly to the American B-29s that served as patterns, with comparable speed, range, altitude capability, and handling characteristics. Soviet engineers are simultaneously relieved that the enormous effort has produced a functional aircraft and amazed that systematic reverse engineering of such a complex machine actually worked. And as additional Tu-4s are built for testing and evaluation, Soviet confidence grows that they have successfully replicated American strategic bombing capability, even though the process required developing new materials, manufacturing processes, and technologies across Soviet industry. The production of the Tu-4 reveals the true scope of Stalin's ambition, because rather than building small numbers for evaluation or limited deployment, Soviet aircraft factories are ordered to produce the Tu-4 in quantity as rapidly as possible, and production eventually reaches several hundred aircraft, making the Tu-4 the foundation of Soviet strategic bombing capability in the late 1940s and early 1950s. American intelligence initially doesn't believe that the Soviets have successfully copied the B-29 because the technical challenges seem too great, and American analysts assume that Soviet industry lacks the sophistication to replicate such an advanced aircraft. But when Tu-4s appear in large numbers at Soviet air shows and in operational service, American military planners must confront the reality that the Soviet Union now possesses strategic bombing capability comparable to American capabilities. The appearance of the Tu-4 in significant numbers alters American defense planning because strategic bombers capable of reaching American territory from Soviet bases in the Arctic or from bases in Eastern Europe that could be established in wartime create a threat that American air defenses must prepare to counter, and the recognition that Soviet copies of the B-29 give the Soviet Union capability to deliver nuclear weapons, which American intelligence knows the Soviets are developing, against American cities, forces fundamental reassessment of American vulnerability. The Tu-4 essentially obsoletes the assumption that America's geographic isolation provides inherent security, and American defense planners must now consider that Soviet bombers could strike targets throughout North America, just as American B-29s had struck targets throughout Japan. The Korean War provides unexpected validation of both American B-29s and Soviet Tu-4s, when American B-29s operate over Korea conducting strategic bombing missions, while Chinese and North Korean forces occasionally deploy what appear to be Soviet-supplied Tu-4s, and American pilots report that the Soviet copies perform almost identically to American B-29s in flight characteristics, altitude capability, and defensive armament. The psychological impact on American aircrews of encountering Soviet aircraft that are exact copies of American designs is significant because it demonstrates Soviet capability to replicate American technology and suggests that technological superiority can't be assumed to remain exclusively American. The Soviet success in reverse engineering the B-29 influences American security practices regarding advanced military technology, because the realization that even highly complex aircraft can be successfully copied if examples fall into adversary hands leads to much stricter controls on where advanced American aircraft operate and much more aggressive efforts to prevent or recover crashed aircraft in areas where they might be captured. The B-29 reverse engineering also influences American assessment of Soviet technical capabilities, because prior to the Tu-4's appearance, American intelligence consistently underestimated Soviet industrial sophistication and assumed that Soviet technology lagged American capabilities by many years. But the successful copying of the B-29 demonstrates that Soviet industry can accomplish sophisticated tasks when resources and political will are applied at the highest levels. For Soviet aviation industry, the B-29 reverse engineering represents a massive force technology transfer that advances Soviet capabilities in metallurgy, manufacturing precision, systems integration, and numerous other technical areas by years, compared to the gradual development that would have occurred through indigenous Soviet research and development. The organizational lessons of the Tu-4 program, including the importance of systematic documentation, quality control, and coordination across multiple industries, influenced subsequent Soviet aviation development programs, and many of the manufacturing processes, materials, and technologies developed specifically for Tu-4 production become standard practice across Soviet aviation industry, benefiting subsequent aircraft programs even after the Tu-4 itself becomes obsolete. Tupolev's design bureau gains enormous prestige from successfully completing Stalin's directive to copy the B-29 within the mandated time frame. And Tupolev himself, who had been imprisoned during Stalin's purges in the late 1930s and had worked on aircraft design while incarcerated, is fully rehabilitated and becomes one of the Soviet Union's most influential aviation designers, leading programs that produce numerous important Soviet aircraft over the following decades. The success of the Tu-4 program validates Tupolev's systematic, conservative approach to aircraft design that prioritizes proven solutions and careful engineering over radical innovation. And this approach becomes characteristic of Tupolev Bureau's work through the rest of the Cold War. The ultimate obsolescence of the Tu-4 comes relatively quickly as jet-powered bombers enter service in both American and Soviet air forces in the 1950s, making piston-engine strategic bombers like the Tu-4 and B-29 too slow and vulnerable to jet interceptors to survive in contested airspace. But by the time Tu-4 production ends in the mid-1950s, the aircraft has served its strategic purpose of giving the Soviet Union credible strategic bombing capability during the crucial early Cold War period when the Soviet nuclear weapons program is developing, and when deterring American attack requires demonstrating capability to strike back at American territory. The Tu-4 never drops weapons in anger except in limited use during the Korean War, but its existence and deployment in substantial numbers forces American defense planners to devote resources to continental air defense that might otherwise have been used for offensive capabilities. The B-29 that Captain Jarrell landed in Vladivostok in November 1944, expecting to be allowed to return to American control, instead becomes the pattern aircraft for the entire Tu-4 program, and this specific aircraft is preserved and measured more carefully than the others because it has less battle damage and is structurally more representative of B-29 production standard, and Soviet engineers essentially take it apart piece by piece while meticulously documenting every component, every dimension, every material, and every manufacturing detail. Jarrell and his crew eventually returned to the United States after diplomatic negotiations, and they report that Soviet troops were generally professional and that they were reasonably well treated during their internment. But they have no idea that their aircraft becomes the template for the Soviet Union's first strategic bomber force. The broader impact of the B-29 examination and reverse engineering on the Cold War arms race is profound because it demonstrates to both Americans and Soviets that technological advantages can be copied or countered given sufficient resources and determination. And this realization accelerates the pace of military technology development as both sides recognize that maintaining technological superiority requires constant innovation that stays ahead of adversary reverse engineering capabilities. The Tu-4 program also establishes patterns for Soviet military technology development that persist throughout the Cold War, including willingness to copy Western designs when Soviet indigenous development lags, systematic programs to examine and understand captured or obtained Western equipment, and the use of reverse engineering, not just to create copies, but to understand Western technical approaches that can inform Soviet indigenous development. The metallurgical advances that Soviet industry achieves in order to produce aluminum alloys comparable to American alloys used in the B-29 have applications far beyond aircraft production, and these improved alloys eventually benefit Soviet automotive industry, construction, and consumer goods production as the technologies developed for military applications diffuse into civilian sectors. The manufacturing precision and quality control practices that Soviet factories must adopt to produce Tu-4 components that meet B-29 specifications similarly influence Soviet industrial practice more broadly, demonstrating that Soviet factories can achieve precision comparable to Western standards when requirements are clearly specified and quality control is rigorously enforced. The human cost of the Tu-4 program includes the tens of thousands of Soviet engineers, technicians, factory workers, and scientists who work under intense pressure to meet Stalin's deadlines, often working extended hours in difficult conditions with the implicit threat that failure will have severe consequences in a system where disappointing Stalin can be fatal. The program represents Soviet industrial mobilization at its most effective and most brutal, demonstrating the Soviet system's capability to accomplish massive technical projects through centralized control and unlimited resource allocation, while also showing the human costs of a system that treats individuals as expendable resources to be consumed in pursuit of state goals. The story of Soviet engineers examining captured B-29s and realizing that American bombing capability was unstoppable unless the Soviet Union could rapidly develop equivalent capability is ultimately a story about technology transfer through reverse engineering, about how systematic analysis and dedicated effort can replicate even highly complex systems, and about how the Cold War competition drove both superpowers to invest enormous resources in military technology development. The B-29 was designed as a weapon to defeat Japan through strategic bombing, but its greatest strategic impact may have been forcing the Soviet Union to develop equivalent capabilities through the most ambitious reverse engineering program in aviation history, and in doing so, accelerating the Cold War arms race and creating the mutual strategic bombing capabilities that characterized superpower confrontation for decades. The Tu-4 represents the last generation of piston-engine strategic bombers and marks the transition point between World War II-era aviation technology and the jet age that will follow. And the fact that the Soviet Union achieved this capability through copying American designs rather than through indigenous development reflects both Soviet pragmatism. In recognizing that copying proven designs is faster than developing original solutions, and Soviet industrial systems' capability to mobilize resources at massive scale when directed from the highest political levels. The success of the Tu-4 program gave Stalin the strategic bombing capability he demanded and demonstrated to both Soviet and American leadership that technological advantages in military competition are temporary, and that determined adversaries can replicate advanced systems given sufficient motivation and resources.